Hey there, and welcome back to your next lesson on higher level mathematics. So we're continuing with geometry today, and today we're looking at circle theorems. So circle theorems are normally quite sort of higher grade problems, quite a daunting topic sometimes for people, and I'm hoping I can help make this clearer and easier to understand. So we've only really got two sections we're going to be looking at today. So just looking at definitions and proofs. So circle theorems, it's a bunch of theorems we have, certain properties about trigonometry inside circles and relationships between various angles and sides that are true when you have something essentially inscribed inside a circle. We need to know what those are and how to prove them. Like as part of the higher course, you can be asked to prove some of them, but like we'll see, a lot of them are relatively straightforward if you know what to look for. And then we're going to look at applications. So this is what you'll mostly encounter, which is like some actual geometric problem of triangles and lines going on inside a circle, and we need to be able to apply the correct circle theorems in order to solve for the unknowns that we're trying to find. So let's look at the first section, definitions and proofs. So we've got various um, circle theorems, and they tend to have names. These are not very fixed names. Like sometimes they can take slightly different names, but it's good to just be generally aware of what they're called, what they're doing. So here, this one is like for an angle in a semicircle. So say if we cut this in half, so you got a semicircle, and we create a triangle with one of the sides being the diameter there, that line going through the circle, through the center. The theorem is this angle, no matter what triangle you pick, as long as it's got one side going through the diameter and the other point, going to some point inscribed on that circle. Basically, inscribed means it goes to a point on that circumference. That angle will always be 90 degrees. So, okay, here's our what's actually going on here. We have an inscribed triangle where one of the sides is diameter. How and this angle will then be 90 degrees. So how do we actually prove that? What we can do is we could draw a line like this. And a key property that we'll use many times is the radial line of a circle. So all these points going from the center out to the edge, these are all radii. So they're all going to be the same. Like a circle, the distance, that's what defines a circle, isn't it? The distance from the center to the edge is always a fixed amount. And so we know those are all the same. So this forms two isosceles triangles. So these two angles will be the same, and these two angles will be the same. And okay, so if we now just use the property of this big triangle we have inscribed in the circle, uh, we know the angles are going to add up to 180. So we've got the angle A, we've got the angle B, and then we've got the angle A plus B. We add all that up, you essentially get 2A plus 2B is 180. So therefore, two lots of A plus B is 180, and so therefore A plus B is 90. So you see that angle up touching the circle, the one we looked at first, which is A plus B, we've managed to prove that that is indeed equal to 90. And this is for a general triangle. So we know no matter what the circumstance here, as long as that one side is going through the diameter, we can see that that angle is going to be a right angle. And we put a little box there. That's like a formal thing that mathematicians do. Like you don't have to do that, but you can if you want. It remarks like end of proof. Like when you've finished a proof, you put a little box and it shows you finished. Um, so let's look at the inscribed angle theorem. So a slightly different one. So that's something like this. If I have a chord and I've got one triangle that goes from that chord up to the center and another triangle that goes from that chord up to an edge on the circumference, specifically in the same direction, not going down. They both have to go in. That's important. Um, you'll find this angle here and this angle here will be similar. Like that one at the center will be twice the one at the edge. Always, regardless of where you put that point on the circumference, that second triangle, it's always going to be double that angle at the center. So, okay, here's what we've got. We've got a chord, and that's the base of two triangles that are inscribed on this circle. Well, except one of them's going up to the center, one going to the center, and one on the circumference. So we have this word subtend. So when it says it, the triangle subtends to the center, it just means it goes up to the center and meets there. So how would we prove that if we didn't know? Again, what drawing in radial lines to our vertices is often a good place to go. So like this, because there's a whole bunch of lines here that we know are going to be the same because they're all radial lines. So that's the important thing when it comes to circle theorems. Don't lose sight of everything else you already know about trigonometry, about circles, about triangles, because you need to apply them as well. You need to use all the skills in your arsenal. So again, we've created isosceles triangles. This is the common thing that's going to keep happening. So we've got this is going to be are going to be equal angles because that's one isosceles triangle. Got another isosceles triangle there. And we can then deduce that this angle here must be 180 minus 2a because all those angles have to add up to 180. This angle must be 180 minus 2b. And so we've now got this third angle here, which we label C. We can work out what that's going to be in terms of A and B, which is useful because you see that angle at the top, the one we were considering, that's A plus B, isn't it? So if we can show that C is equal to 2 lots of A plus B, then we're done. And so, okay, using the fact that all those angles in the middle must add up to 360, because it's a full circle, we've now got an expression in terms of an equation in terms of C, A, and B. And we can just rearrange this to make C the subject. So if I expand out those brackets, collect together my number terms, if I subtract that from both sides, I've got C is equal to 2A plus 2B. So C is equal to 2 lots of A plus B by just factoring out the 2. So that's end of proof. Because we've shown there that that angle at the center is double the angle at the top. So that's how you'd prove something like that. You see so far, all we've been doing is basically just drawing in radial lines, creating isosceles triangles, and then, using the fact that the angles add up to 180 degrees and a full circle is 360 degrees. It's a lot of basic stuff that we've already done. It's just a matter of being able to see that path. And if you can't see it, with these kinds of questions, what I would often say is just put in whatever information you can put in. So put in what you do know, and then as you start putting in more and more information, it might start to come clear the path you need to take to get to the answer. So yeah, drawing radial lines, that's a good place to start. So now we've got the next one, angles in a segment. So that's when you have like this a chord. You've got a triangle that goes up to the circumference that has that chord as a base, and then another triangle that goes up in the same direction that also have that chord as a base to another point on the circumference. And what you'll find is both those angles are the same, no matter where you put those 2 points of the triangle on the circle. As long as they're going up, in one direction away from the chord, it will always be the same. So yeah, we've got the chord that's the base of 2 triangles. Both triangles are subtended from this chord to a point inscribed on the circumference of the circle. Of the circle. So yeah, again, make sure you're comfortable with what those keywords mean. Subtended means it's going up from that chord, and inscribed means it's on the circle. So okay, if we didn't know that, how would we prove that? This one is very straightforward, from our previous theorem. So we can use other theorems to prove this circle theorem. So if we draw this line up to here, you see here we've got now another triangle subtending from that chord, but going up to the center. Using the previous theorem, these two angles A and B, the inscribed angle theorem, we know that C is going to equal to 2A, but it's also going to equal to 2B. So we can use that theorem on both of these because they're all sharing the same chord. So C must be double 2A, but it also must be double 2B. So this means 2A must be equal to B, and therefore A must be equal to B. The only way this could work. So there you go, very simple proof to show that. Now we're looking at what's known as a cyclical quadrilateral. So a quadrilateral is a four-sided shape, and we've seen that before. A cyclical quadrilateral is one like this, a quadrilateral that is inscribed inside a circle. Doesn't have to be going through the center or anything like that. It's just 4 points on the circle. You connect it up, create a quadrilateral. And we've got a quadrilateral that's inscribed in a circle. And so, yeah, what we're trying to prove here, I haven't put it in, but it's basically the opposite sides of this quadrilateral will always add up to 180. No matter where these 4 points are, the opposite ones will add up to 180. So let's see how we do that. Again, like we kind of usually do, drawing your radial lines to various vertices because we know that they're going to be equal, which is useful information. We could draw this chord going along here. So just generally joining up vertices can be a good place to start, see what happens. So using the inscribed angle theorem, we can relate these angles to the angle at the center. So you see there, that dashed line, I've created a triangle there where there's a chord subtending to the center of the circle, but you also, from that chord subtending down to the circumference, there's another triangle, isn't there? And using that theorem, we can see that that angle at the center is going to be twice that one on the edge. Now, the interesting thing is about this is you can do it in reverse as well. So this angle here, this big reflex angle, is going to equal to double that other angle at the top. So you see that inscribed angle theorem. Normally it's where triangles going in the same direction. Here we've got a triangle like one pointing down, one going up. It's like that outside angle, the exterior angle of that triangle, would then be the same as that triangle going in the other direction. We can prove that in a very similar way to the actual inscribed angle theorem that we've already seen. So sometimes, yeah, we need to use that as well, that you can kind of do it in reverse like this. It's a bit weird because you get this reflex angle, but it does work. So rather than, like an obtuse and an acute angle, which we've got in green, you've got an obtuse and a reflex, which are in blue. Now we can just use the fact that that full circle in the middle is going to be 360, isn't it? So 2a plus 2b is 360. So a plus b is 180. And you see a plus b are those opposite angles of the quadrilateral. So a plus b is equal to 180. And we showed this for a general case. It doesn't matter where those points are. So this will be the same in all cases. And we can do the same thing if a similar thing to show that the opposite angles left to right are also the same. It's essentially the exact same process. So there we go. That's the cyclical quadrilateral theorem. Now we're looking at chord radius theorem, which is something like this. When you have a radius and we have a chord. And if that radius and chord intersect at a right angle, that only occurs if it bisects that chord. And bisecting meaning it chops it into two equal pieces. So those two lengths are going to be the same. And that works in both cases. So if you've got if they intersect at a right angle, then it's going to bisect it into two equal pieces. But also, if it bisects it into two equal pieces, it means it must be intersecting at 90 degrees. So you can kind of apply that in both directions. So a radial line meets the chord, will bisect that chord if it's 90 degrees. Yeah, it works both ways, like I said. And how we can prove that is by just doing something like this. Again, drawing radial lines. You can see these two are going to be the same. I've used the double dash because they're going to be the same as each other, but not necessarily the same as those two lines making up the chord. And so if that's a right angle, we know that's essentially, the height of that isosceles triangle. The only way that's a right angle is if it's the height and going straight down the middle of it. In which case, that bottom, the base of that triangle, which is the chord in this circle, must necessarily be chopped in half. So we can sort of see that quite easily. It's kind of more almost from definition, really. So this is not something you'll really be asked to prove. It's almost that sort of, yeah, like I said, from just definitions of isosceles triangles and that. So now let's look at the tangent radius theorem. Again, this is one of those things you won't be necessarily you won't be asked to prove, really, because it's kind of more by definition. But you can see it from this. Like, imagine if I had this scenario and I slide that line down to the point where it just touches the end of the radius, just the tangent to that circle. Because I've just slid it down, like straight down, like I haven't tried to change the line, the angle's not going to change. It would still be 90 degrees. So even at that point where it's just touching the circle, it's also going to be 90 degrees. So that leads us to the tangent radius theorem, which is that a radial line and a tangent line, if they come to a common point on the circumference of the circle, it's going to do so at a right angle. And you can kind of, see that's going to be the case. So finally, well, no, not finally. Finally, regarding tangents, if we have a tangent theorem, which is when you have two tangents like this, you're going to get these two lines here from that point where the radial lines meet that tangent point to where the two tangents intersect. They're going to be equal lengths, and we can see why that is. So we have two tangents that intersect. The distance from the tangential point to their point of intersection is going to be the same for both tangents. So that's what the actual theorem is. And we can see that if we draw this line here, now these two are radial lines again, so we know they're going to be equal to one another, but not necessarily equal to those other lines, the tangent lines. And that line going from the intersection point to the circle, the point on the circle, center point of the circle, sorry, that's a common line for both triangles. So, and we know they both meet at right angles here. So, okay, let's think back to our trigonometry. What we've got here is we've got two triangles here that have two sides in common, and they have an angle in common. Well, those are both basically going to be the same triangle. Like we learned from trigonometry that is enough information to calculate all the other sides and angles of the triangle. And because those sides and angle are the same in both of these two triangles we've created here, they're going to get all the same value. So bottom line is these are both basically the same triangle. They're congruent triangles. You see one of them's basically just been flipped over. And because they're the same triangle, therefore those two sides will be the same. And in this little drawing we've made with these two triangles, those two angles, other angles would necessarily be the same as well. So if you have a scenario like that's what's going to happen. So yeah, you see this kind of scenario here, it just divides things up into two congruent triangles, and so if all sides and angles are going to be the same. So okay, let's look at the alternate angle theorem now. So we're looking at some more tricky theorems now, trickier to prove at least, not so tricky to necessarily use. So say if we have a triangle like this, just a general triangle inscribed inside the circle, and we have a tangent meeting one of the points of that triangle. Alternate angle means the angles at the that tangential point and the other angles in the triangle on alternate sides, as in interior and exterior, are going to be equal. So one example is these two here. So you see at that tangential point, you've got like an exterior angle to the triangle, and up on the top, the triangle in the angle inside, like the interior angle of the triangle, they're going to match. And that works in vice versa as well. Like these two as well are also going to match. Um, so how do we prove that? So let's clearly define what we're doing first of all. So we've got a triangle inscribed. A tangent line touches the circle at one of the inscribed points of the triangle. Those then angles will be the same. Just remind yourself these are the angles that are matching. Now we need to prove it. So it's a little bit tricky, this one, but let's do some labeling, A, B, C, like this for the three points on the triangle. And what the key to this problem is drawing this diameter straight through the triangle. And we could connect these two lines up here. We can put the point D here, and I'm going to put points E and F here on either end of the tangent line, just for ease of explaining this. So we need to use various properties of your triangles and tangents and that we've seen so far. So first of all, we know this is a right angle here. That diameter is going to meet the tangent at a right angle, isn't it? Also, we know this is going to be a right angle, isn't it? Because that triangle ACD is a triangle where one of the sides of the triangle is the diameter, isn't it? So that angle there we know is going to be 90. So okay, if we now label this angle here X, we can deduce that this angle here is going to be 90 minus X, because you see that triangle ACD is the angles are going to add up to 180, aren't they? So we see 90 minus X has to be that remaining angle down there for this to all add up to 180. But you see that little sliver angle we've got there, 90 minus X, plus the remaining part of the angle that makes up that CAF, that remaining part adds up to make 90 degrees, as we can see there, because it's a tangent point. So we can tell that this is going to be 90. Sorry, this is going to be X. So X plus 90 minus X is going to add up to 90, won't it? So now finally what we're doing is we're using the inscribed angle theorem. And from that we can deduce this angle here will also be X, because we've got the chord AC. And we have AC subtends to the triangle ADC, and it subtends to the triangle ABC. And so we can see those two angles at the points D and C of those two triangles are going to be the same. So we've now managed to show that the alternate angle theorem works. And very quickly, I can show you the same thing in reverse, like on the other side. So we have this angle is 90 degrees, it's going to be exactly the same way. So this angle here is also going to be 90. And if we label this angle y, we can deduce this here is going to be 90 minus y. Therefore, this angle here will be y. And then using finally the fact that we have two triangles there sharing a common chord, BA. So we've got BDA is one triangle and BCA is another triangle. They're both going to have the same angle. And so therefore we've shown those two alternate angles are also going to be the same. So a little bit more going on there, bit tricky, less likely to be asked to prove this one. Normally actual proofs, they ask the easier ones. Now, finally, last one is the intersecting chords theorem. So that's when you've got something like this, just two random chords and they're intersecting. Now, this is a very advanced one that you only really get asked about on real sort of top grade questions. So if you're gunning for like top grades, you really want to make sure you know this one. So we have an intersecting point, say if I label that I, and these inscribed points, B, C, D, I'll label that. And then the lines going from those points, say if I label them A, B, C, D. So the little a is basically the distance A to I, the little b is distance B to I, and so on and so forth going around. So for any two chords, the four distance created will satisfy this equation. So you see that line AC that is split up into the two parts, A and little c, and then the line BD, which is split up into the little b and little d. AC will equal BD. Now, how do we prove something like that? So for something like this, what we do is we need to find similar triangles. That's the key to this problem. And if we draw lines like this, you can see that if we create this base here, BC, you see we've now got two triangles, BAC, BDC, that both share the common chord base. So these two angles are going to be the same. Likewise, we can draw this common chord base for the two triangles ABD and DCA. Those two triangles are going to have a common. So using the fact that we've got two triangles sharing the same base, we know these angles are the same using our previous circle theorems. Now, using the fact that just two lines that cross opposite angles equal one another, don't they? Because it's essentially like symmetric. And so look at what we've got here now. We've basically got two triangles that have all the same angles. And so that means these are similar triangles, like what we've seen before. If you have two triangles and the angles are the same, that means they've just been scaled up and down, like the distances have been scaled. Because that's the only way that the angles would stay the same. Like if you've actually sort of times one, made one distance, bigger and kept the others the same, say, the angles would then alter. So we've got similar triangles here. So what that means is various distances have been scaled by some scale factor. So say if we look at the distance between the blue angle and the red angle in each triangle, that's A and D. They're just going to differ by some scale factor, K. So A will equal to K lots of D. Similarly, if we look at the side between the green and the blue, basically the B and the C, B is also going to equal to that same scale factor times C. Because we're scaling up all sides by that common factor. Therefore, we're pretty much done now. So what we want to do is cancel out the k, and we can do that by just simply doing a divided by b. So that's going to be kd divided by kc, and we cancel out the common factor of k. We've now got ab equals dc. Sometimes this is presented as the intersecting chords theorem. I prefer putting it in this form where I just cross multiply the c and the b. And so that's then the end of the proof. So you see there, when we've got something like this, intersecting chords, we can often create similar triangles. And that's the key to then finding these distances. Like, right, okay, so we've already spent quite a long time on that. So we've introduced all the different circle theorems and proved why they are the way they are. I don't think you'd ever be asked be asked to prove the intersecting chords theorem, because that's already a very advanced theorem. Normally, it's just you have to use it. Um, so let's look at some applications. So first of all, this example. So we start with a simple one and gradually work up to harder ones. How would we do this? Now, this one, actually, you don't even have to use circle theorems at all. So this is something I want to reiterate. Make sure you don't lose sight of everything you already know, like about trigonometry and circles and, geometry in general. It's not all about the circle theorems. So here, you see here, because we've got two radial lines, AO and OC, they're both equal. So therefore, that's an isosceles triangle, and the angle at A and the angle at C are going to be 22. So we have the same thing going on in the triangle OBC. The angle at B and the angle at C, though the x plus the 22, have to be the same because OC and OB are radial lines. So it's another isosceles triangle. So therefore, we get a little equation for x. X plus 22 must equal 67. So therefore, x is equal to 45. So yeah, very simple one there. Just using the properties of a circle and isosceles triangle. Let's take a look at this one. So straight away, you should see, look, we've got a cyclical quadrilateral, so that will probably come into play. But you can also see if we just draw a radial line, not a radial line, a chord from D to B, we've now got two triangles subtended from that chord. We've got BOD going to the center, BAD going to the circumference. Well, we know that one at the circumference is going to be half the one at the center. So we got that as 78. Now we can use the fact that opposite angles in a cyclic quadrilateral add up to 180. So 78 plus the x must equal to 180. And so we can that allows us to then work out what the x is going to be, which is 102. Alternatively, you could have seen that this other angle here at the center is going to be 204 because it has to add up to 360 in total. And then you could use the fact that, DB is a shared chord of DOB and DCB, but they're kind of going opposite directions. So we'd have to use that reflex angle there, wouldn't we? So x would be half of 204. 2x is equal to 204. So x is half of that, 102. So you see, either way you work it out, perfectly fine. You see, you get the same answer, and that's important. So another example is one like this. So first things first, looking at this, straight away, you got to see like what things can fit here. The first thing I see is that we've got a big triangle, ABC, with one side being the diameter. And that tells me straight away that that complete angle at B, like x plus that little sliver, must be 90 degrees. So I could use that to then find out what the angle at A is going to be. Because that 90 degrees plus the 34 degrees plus that remaining angle at A has to come to 180, sorry. So therefore that angle must be 56. Now that other triangle we have, AB to then that other unlabeled point at 61 degrees. That triangle, we can just use the fact that they must all add up to 180. Therefore, we've now got a little equation for x that we can just solve. And we find x is equal to 63. So that's using the fact that a triangle with one side being the diameter, we can tell one of them is going to be 90 degrees. Now let's look at one like this. We've got a tangent problem here. AB is a tangent. It's meeting the radial line OB at the point B. And we've also got the line AOC is one just straight line. There's no like kink in that line. It's just straight. What would we do here? Again, let's just put in whatever, like the usual information. So straight away we know this is a right angle because it's a tangent line meeting a radial line. We've also got the fact that this is going to be 44 now because we've got the triangle ABO is, well, it's a triangle, so they all add up to 180 degrees, all the interior angles. So so that must be, 90 minus the 46, we'll get 44. We can also use the fact that BOC is an isosceles triangle. So therefore this angle is going to be this at B is going to be the same as the one at C. So our unknown x, because it's an isosceles triangle. So therefore, this angle here, even though we don't know what it is, but we can put it in terms of x, it's going to be 180 minus the other two angles, which is 2x. And now you might be able to see we can create um an equation for x and solve, because AOC is a straight line. So 44 plus the 180 minus 2x is going to be a straight angle, which is equal to 180. So we've got 180 minus 2x plus the 44 is equal to 180. So if I cancel out the 180 on each side, I've got minus 2x plus 44 is 0. 2x is equal to 44. Therefore, x is equal to 22. So that's kind of what we're often doing, like with this. We need to use our circle theorems or general properties of triangles and whatnot, um, to produce some kind of equation for our unknown. And then it's just a matter of solving that equation. And oftentimes it is just a simple linear one like this, but not always. So say if we look at one like this, this will be our final example. So when you've got a scenario like this, where we've got two straight lines, so DAI is a straight line, CBI is a straight line. So again, there's no like kink at those points A, B, it's just straight. And you see how that line has been split up. Um, like DI, you've got X and 16. IC, we've got 5 and 11. So when you've got a scenario like this is it might seem similar to the intersecting chords problem, but this is like if you're getting like a proper high grade question, this is something examiners love to ask, because it is an intersecting chords, but it's extending outside the circle. And that does make it a bit trickier, but we can apply the same logic like we did earlier. So um, let me show you how this works. So say if we draw a line like this, AC, and we draw a line like this, BC. Now, you see, because this is forming two triangles that share the common chord AB, we can see these two angles are going to be the same. And we're also creating two triangles with a common chord DC. And so that means these two angles are going to be the same. So you're basically triangles sharing a common chord, subtending to 2 points on the circumference. Now, using again the fact that two lines, straight lines crossing, opposite angles are going to be the same. So these two angles are the same. So we've got two similar triangles here. But that is not so useful for us because we're not looking for the dashed lines, the lengths of those dashed lines. But there are two other similar triangles that we can work out here, which is the triangles IAC and the triangle IBD. So you see those two triangles, really long stretched triangles that are extending outside the circle. So we can see they've got the common angles at D and C first. They're also going to have this common angle here where they overlap. But also we get these two angles they have are also going to be the same, because we showed that those two other angles, those two little slivers at A and B, are the same, and together they make a 180 like straight angle at the points A and B, and so therefore these two pink angles must also be the same. So yeah, take a second to sort of see what's going on there. We've got two overlapping triangles there, IAC and then IBD. Two triangles, and you see they've got all the same angles, so they're similar triangles. These two triangles here, and let's bring them out like this and label their sides accordingly. So sometimes this is something good to see, so you can see them side by side. Just make sure you label the sides correctly. And because they're similar, we know x plus 16 is just some scalar multiple of 16. 5 is just then going to be the same multiple of x. And so therefore, if we do x plus 16 over 16 and 5 over x, that that scale factor is going to cancel out. We've got basically 5k times by xk. That factor will cancel out. So so you see, first of all, those two triangles, you make sure, you can see those side lengths are going to be correct. Like the long ones, like IAD is basically x plus 16, isn't it? And then IBC is 5 plus 11. So that's where the 16 comes from on that triangle. So that's the key step. We're using the intersecting chords theorem there, essentially. And now, all of that was basically just to produce this equation of x. And now we can just solve, which is an algebraic fraction problem. So that's what often makes this, quite challenging as well. It's using some advanced algebra. So we have to solve that in the way we normally do by cross multiplying, uh, multiplying out the two denominators. We produce actually a quadratic, and so now we've got to use our quadratic skills as well. Which in this case we can just factorize. It's not too bad, and we get two solutions: x equals minus 20, x equals 4. Now immediately we can just cross off minus 20 because you can't have a negative distance. So the answer is x is 4. So like I was saying, very advanced problem. Now that is very much like a grade 8 or even grade 9 problem. Um, Probably more like grade 9 really. But yeah, you need to be comfortable using this theorem because it can be asked. Uh, but it's quite uncommon. Alternate angle is normally about as hard as it gets. So, but you see, it's applying the intersecting chord theorem in a different way because the chords were intersecting outside the circle. So, um, like what I often like to say, perhaps you've heard of the phrase of thinking outside the box. Sometimes here you got to think outside the circle. But you can see it's doing very similar things. So that's it. That's it for circle theorems. Um, so, did you know that circle theorems have many interesting uses? Architecture, physics, astronomy, anything that's going to require uh, geometry and understanding, tangents and triangles, circles. One example that I'm very familiar with, which is if we're dealing with, say, on the surface of the Earth, and say if you had two people here at two different locations, A and B, a tangent line would be essentially like their horizon. It's like as far as you can see, because all we can see is essentially in a straight line. We can't see round the curvature of the Earth, can't we? Um, and B is going to be the same. And so you imagine if we've got like a satellite that's orbiting around the Earth, we can then tell who's going to be able to see it at what times, depending on, by using circle theorems. So here at this point, it's like A can see this satellite. And now we're getting to the point where the satellite is about to set below A's horizon. And now it's going to rise above B's horizon. And now B can see it and communicate with that satellite until it goes eventually over its horizon again in the other direction. So yeah, that's one uh, use of circle theorems. We get, we can then calculate where those points are going to be. So here we go. Here's our takeaways for today's lesson. So that's just all the circle theorems. It's just one topic that we've just managed to do in that one lesson. So next time we're going to wrap up geometry now on two kind of different but related topics, smaller topics, loci and vectors, but mostly vectors. Vectors are very, very important. You don't do too much of vectors at GCSE, but they are a big, big topic in mathematics, and they're used in so many different ways. So yeah, I will see you next time for a study on loci and vectors.